I'm going to just jump right into the topic. Again, if you can't hear me, let me know at the back. So today's lecture is going to deal with what neural networks are. In the introductory lecture, we had an idea of, well, let me correct myself. In the introductory lecture, we went through some quick discussion of what is a neural network at a very, very high level. But then what can these things actually represent? So let's go through a quick recap of what we covered in the last class. First, we observed that neural networks have become the state of the art in many AI-related tasks like speech recognition, machine translation, playing smart games, driving cars, sticking captions on pictures, even being creative. Now, the thing about all of these tasks is that for a very, very long time, these were thought to be strictly in the domain of human expertise. Machines were not supposed to be able to do this, right? And then neural networks came along, and they show us that they can not only do this, they can actually do it very well. So what are these neural networks? They are essentially functions. There's a box, something goes in, something comes out. Every one of these tasks that we saw is really just the machine that performs every one of the tasks that we saw is just a function. It takes some input. It could be sensory. It could be a voice signal. It produces a transcription. It could be an image. It produces a text caption. It could be a game state. It produces a next move, but it's a function. So what's in these functions? And as we saw in the last class, to motivate the design of these functions, we went back and consider that these tasks are fundamentally human, right? And in the case of the humans, again, these are just functions, but the machine mechanism that's performing these functions is the human brain. Our intelligence, our consciousness is powered by the brain. So when we begin building neural networks, the original intention was to somehow try to emulate the structure of the brain, because obviously the brain is able to do it. Now, if you look into the brain, we saw in the last class, here's what the brain has. It has billions and billions of neurons, all of which are connected in one gigantic network. So did we cover how many neurons there are in the human brain in the last class?
Tens of billions.
There's of the order of, so can someone give me a precise number? Pardon me? 10 billion. Better than that? You're getting close, within an order of magnitude. The estimates are between 80 and 100 billion neurons in the head. So that little thing on top of your neck, it's carrying a lot of stuff. Now, each of those neurons has this structure. You have all of these structures at the end, the dendrites, through which they get signals from other neurons. If the total signal exceeds the threshold, this neuron fires that signal and down the axon out to other neurons, where it feeds other. So our computational model too is going to sort of emulate this structure. The basic unit is something that emulates the brain. It's what we call the perceptron. And starting with this basic unit, we again emulate the structure in the brain where a lot of these neurons are interconnected, and we connect these up into networks of these computational equivalents of neurons, of these perceptrons. So let's look at each of these quickly. Again, we've done this in the last class. This is just for a quick recap. So each of these guys was performing something very similar to what the neuron in the brain performed. It gets a collection of inputs. It computes a weighted combination of all of these inputs. And if the weighted combination exceeds a threshold, it fires a 1. Otherwise, it does not fire. So the output remains 0. So if I write it out in arithmetic, here's what it's going to look like. The weighted sum of the inputs is computed out here. If that exceeds a threshold, this is going to fire. The output is 1. Otherwise, it's a 0. That's, again, very analogous to how the neurons in the brain were originally conceptualized as. These are actually what electrical engineers will call threshold gates. We'll get back to that. So I'm going to redraw this figure just slightly for mathematical convenience, but this is going to be important. Instead of saying that the weighted sum of the inputs must exceed a threshold, I can say that the weighted sum of the inputs minus the threshold must be greater than 0. It's exactly the same operation. So now I can define this variable z. Z is the affine combination of the inputs. So what's the difference between being affine and being linear? Anyone? Yes?
A linear combination has 0, 0 as a solution generally, and an affine combination.
Anybody? Yes?
The hyperplane that represents this doesn't pass through the origin?
So from this, that's correct. Both of you are right. From this perspective, if I got rid of this t, it's going to be a linear combination. If I have the t, it's affine. There's a formal mathematical definition of linearity. Anybody remember that? Yeah. Yes.
Superposition, that's additivity. And
so if I take a linear function, if I have f of x1 plus f of x2, that's going to be f of x1 plus x2 for linearity. That doesn't hold for affine functions. So this is not a linear function. This is an affine function. You must remember this, because if you think of this as linear in some situations, this is going to come back and bite. But anyway, we compute an affine combination of the inputs. If that exceeds a threshold, if that's greater than 0, the neuron fires. So it's the equivalent of saying that I have a function f which operates on this affine combination of inputs and produces an output. And that function f is the simple threshold function. When the input is greater than 0, it outputs a 1. If it's less than 0, it outputs a 0. But then once you think of it this way, you can make some other modifications. We can replace this strong threshold function with something that's softer, right? So instead of having something like this, I can make it like so. And it's only a minor modification. It's still performing effectively the same operation. But once you relax this condition and say I can put something that curves, I can begin introducing other kinds of functions in this box, like these guys. So this one is a sigmoid. The tan h is just a shifted sigmoid. You have these other guys. This one here is a hinge function, often called a rectified linear unit. You have the softer version, the blue curve, which is called the soft plus. But all of these are different functions that could operate upon the affine combination of inputs to produce the output. So now, for this lecture, I'm going to continue assuming threshold activations. This function here is what we will call an activation function. An activation function is what operates on the weighted combination of inputs to produce an output. We're going to continue to assume threshold activations. But then that was just the basic unit. The brain itself is a large connection of these guys. So we're going to try to emulate that. We're going to take lots and lots of these units, and we're going to connect them up into one gigantic network. Typically, these networks, for computational convenience, we like to make them layered, meaning you have one layer of units, and one layer connects to the next layer. So if I call this layer 1, and this is layer 2 and layer 3, layer 1 doesn't directly connect to layer 3, it connects to layer 2. So these are typically layered structures. You won't always follow the structure, but this is the simplest structure that you can think of for computational purposes. Now, when you speak of neural networks, these days everybody's talking of deep neural networks. So what does it mean for this network to be deep? Depth has it's not just hand waving. Depth has a very nice formal definition. And we say, and depth is defined in the context of graphs in general. So anytime you have a graph of this kind, if you have a directed graph with a source and a sink, then the length of the longest path from source to sink is the depth of the graph. So over here, what would the depth of this graph be? Don't look at the text, just look at the figure. Right? So that's 2, because the longest path is this one, goes from here to here and back down here, right? This guy, although there's a path which is just length 1 from source to sink, the longest path is 1, 2, 3. So the depth of this network is 3. So you get the notion of depth. And when we speak of a deep neural network, we are speaking of layered structures. But even if it isn't layered, we are saying that the depth of the network is at least 3. It's got to be greater than 2, then you call it a deep network. This is just a formal definition of what a deep network is. So that's not very deep. 3 is not really very deep, but still, as far as definitions are concerned, that's deep. So here, for example, this is exactly, the depth is exactly 3, right? Now, yes?
Is the network acyclic?
Pardon me?
Is the network acyclic?
No, yeah, these are acyclic. We won't get into cyclical networks till halfway through the course. And we'll only spend very little time on cyclical networks, right? Now, so you have this network, but then the network is really performing functional operations. Just as we said, every single operation that we saw, whether it was, you folks at the back, do you mind shutting your laptops? Please shut your laptops. Yes. So we saw that in each of these functions, some input comes in and some out, and then you get some output. The inputs could be real or they could be Boolean stimuli. The outputs could be real or Boolean values. You can have multiple outputs from a single network. In fact, that was one of the novelties that Alex Bain introduced historically back in 1873, if you will remember from class 1. So given that it has this structure, and remember, each of these units is really very, very simple. So given that you're taking all of these really simple units and composing them, what kinds of functions can these networks actually compute? What input-output relationships can this network model? And we saw in the last class that these networks can model any Boolean function. You remember that, right? We also saw that it can model any one-dimensional real-valued output. Now, what are the limitations? When I say any, do I really mean any? Is there any restriction on the network structure itself? So that's what we're going to cover for the rest of today's class. We're going to look at now this network structure that we just saw. It's many layers of perceptrons connected to each other, so we're going to call it a multi-layer perceptron. We're going to look at them. We're going to show how these are universal Boolean functions. We'll see that these are universal classifiers and that these are universal approximators, and we'll look at some of the limitations. So let's look at the MLPs as Boolean functions first. How well do multi-layer perceptrons model Boolean functions? You saw this in the last class. A single perceptron can perform all 3 basic Boolean operations, right? So how many didn't see that? Anyone who missed that bit? So just to be clear, in this figure, these are the inputs. X and Y are the inputs. 1 and 1 are the weights. And 2 is the threshold that you're applying. So if X times 1 plus Y times 1 is greater than or equal to 2, the output is 1. And then you can see over here that in this case, the output is only going to be 1 if both X and Y are 1. If either of them is 0, then the total combined input is less than 2. This unit is not going to produce a 1. So this is an AND gate. This is just a simple perceptron that's performing the operation of an AND. Here the weight is minus 1. So now if X is 1, 1 times minus 1 is minus 1. So that doesn't exceed the threshold 0, so the output is going to stay 0. On the other hand, if X is 0, 0 times minus 1 is 0, which matches the threshold. The output is going to become 1. So this is going to negate the input. This one here is an OR. The threshold is 1. If either X or Y are 1, then the total weighted input into this circle is going to be 1. So that matches the threshold. The output is going to be 1. So clearly, this perceptron can model any simple binary Boolean gate. In fact, it's much more powerful than that. So here, for example, it's a universal AND gate. I can say, for instance, that I want this perceptron to fire only if x1 through xl are all 1 and if the remaining inputs are all 0. If any one of these inputs is flipped, I do not want it to fire. That's a fairly complicated function, right? But you can see how I do this. The threshold is L. Now if all of these are 1, the total input they're going to produce is L. If any one of the remaining is also 1, that's going to subtract from the total. And so now the total input that comes in becomes less than L, it will not fire. The only condition under which this is going to fire is if the first L inputs are 1 and the subsequent L inputs are all 0. Right? So, yes?
What if, so the subsequent inputs cannot they take the value of 1?
Pardon me? So think of these. If any of these are 1, 1 times -1 becomes -1. So it's going to reduce the input, right? Similarly, I can have the universal OR gate. I want this perceptron to fire if any of these if any of these guys are 1 or any of these guys are 0. Now you can see how that is done, right? Let's consider the condition under which this should not fire. The only condition under which this should not fire is if all of these first L guys are 0 and the subsequent n minus L guys are 1, right? That's the only condition under which it should not fire, if it's an OR. And under that condition, these are 0, so they produce no input. These are 1, so the total input is going to be L minus n. I want the threshold to be just more than that. So the threshold is L minus n plus 1. This guarantees that this will fire under the condition that we've stated if any of the first L components are 1 or the subsequent n minus L components are 0, right? So it's pretty powerful. Here's something even more magical that it can do. It's a majority gate. So I can say fire, oh shoot, these should have all been 1. I'll fix this on the slides. Hira, can you take a note? This I have a mistake on the slides, right? So if assume that all of these weights are 1, then if I use a threshold of k, this is also wrong, right? Then if k of the inputs are 1, it's going to fire, correct? So this means that I can say fire if the majority of the inputs are on, or fire is some x% of the inputs are on. It's a very powerful function, and you can do it with 1 neuron, right? Still, we saw we can't do an XOR. And we'll see why you cannot do an XOR in a few minutes. But then, if you connect a bunch of these guys in a network, you can perform an XOR. And the way you would do it, this is X, this is Y. You have this one perceptron computing X or Y. This is computing not X or not Y. I AND the two. I'm going to get X, X or Y. So if I just take a bunch of these guys and connect them up in a network, I have 2 hidden neurons. We call them hidden because you're not going to see their outputs. The only output you're going to see is from the AND. So any intermediate outputs that you don't see are called hidden. And so those are hidden neurons. If you connect them up, you can perform the XOR. And so we saw that doing this, we can now begin building up more complex networks. You can get tedious functions like this guy, right? So MLPs can compute any Boolean function. They can emulate any individual gate. So these are what are called universal Boolean functions. We are calling them universal Boolean functions because if you give me an MLP, if you give me a Boolean function, I can always build an MLP that will compute it. It's a universal Boolean function. But then, here's the question. How many layers does this guy have? Anyone? It's got 3 layers, right? So how many layers will you need for an arbitrary Boolean function? Yes? Pardon me? 2?
You need to reduce the Boolean function to its simplest form, and then how many other terms you have, those many.
Yeah, so both of you are right? So you can do this with just one hidden layer. Why is that? A Boolean function is just a truth table, correct? I can write the set of all combinations of inputs on the left-hand side and their corresponding outputs on the right-hand side. I don't need to list all 2 raised to n combinations. I only need to list the combinations for which the output must be 1. So this is my entire truth table. For the remaining combinations, the output is 0. But this guy, this truth table can be expressed using a disjunctive normal form. So what this truth table is telling me is that the network must produce a 1 when x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0, which is the Boolean equivalent of saying not x1, not x2, x3, x4, and not x5, right? So I can have, for every row for which the output is 1, I can add one such clause. I OR the lot, the pluses represent OR, and this is a disjunctive normal form which computes this truth table. Now, given that I can do this, what would the MLP look like? I'm going to have one perceptron for each of the classes. And then eventually I'm going to have one perceptron doing the final OR, and voila. Using just one hidden layer, I can compute pretty much any Boolean function. So given this, why do you need depth? Well, the question is, okay, if I'm going to do this with just one hidden layer, how many neurons will that hidden layer require, right? So a one hidden layer MLP is a universal Boolean function. The problem really is the number of perceptrons that you will require in that single hidden layer if you have n input variables. So to understand how bad it can get, I'm going to use a different representation of the truth table. How many of you are familiar with Carnot maps? Right. Anybody who's an electrical engineer knows what a Carnot map is, right? And if you're a computer scientist, although this is a CS concept, you might not have encountered it, which is very paradoxical. But then this guy here, this box, is a box defined on 4 variables, W, X, Y, and Z. So there are 16 cells because four binary variables can combine in 16 different ways. So here, these are all combinations of Y, Z, 0, 0, 0, 1, 1, 1, 1, 0. These are all combinations of WX, 0, 0, 0, 1, 1, 1, 1, 0. So every cell over here is a unique combination of the inputs. And I've highlighted the cells for which the output is 1. So basically this is a truth table which has 7 rows for which the output is 1, and the remaining 9 rows have an output 0. Everybody clear? Now there's something very magical about how this box is designed. If you look at any 2 adjacent rows, or adjacent columns or adjacent rows, they differ in only 1 bit. The edges connect. So this is actually a cylinder, meaning this edge connects to this edge. This guy and this guy are neighbors. It also connects top to bottom. So this row and this row are also neighbors. So the whole thing is a toroid. And now let's look at this function, right? This function has 7 clauses for which the output is 1. So if I did a simple, very naive DNF formula, how many clauses would it have? 7, right? But then look at this. I can group these things up. If I group it, anytime you have boxes which are adjacent, you can group them up. And this group is telling me that it doesn't matter what W and X are. So long as Y and Z are 0, 0, the output is always 1, right? So in other words, this group is a single clause which is not Y, not Z. Similarly, this group tells me that, regardless of whether Z is 0 or Z is 1, so long as Y is 0 and WX are 0, 1, the output is 1. So this group is the clause not W, X, not Y. And this third one, I'm being suboptimal here. I can group these 2 guys here because they're neighbors. And that's going to give me a clause not X, Y, not Z. So long as you have adjacent guys, you can group these things up. And then you're going to end up with a DNF formula which is reduced. And so if I want to compose an MLP for this particular truth table, all I have to do is to express it as a reduced DNF formula. And the Boolean network for this function is going to need only as many neurons in the hidden layer as there are DNF clauses in the minimal DNF formula for the truth table. Now keep in mind that when I give you a truth table, finding the smallest DNF formula for the truth table is an NP problem. It's not really easy. But still, if it exists, it does exist, and the number of neurons you're going to require in the hidden layer is just the number of clauses, right? What is the worst case? Anybody? What is the worst case for a truth table of this kind? Pardon me?
There are no groupings.
2 to the power n.
So, almost, right? What arrangement of 1s and 0s simply cannot be reduced further? Yes? Yeah, thank you, right? There you go, right? Once I do this, there's no way I can group things. And if I cannot group it, how many neurons will I require in the one hidden layer? In this case, I'm going to require 8, correct? So suppose I have the three-dimensional, or this is actually, this is the three-dimensional equivalent of the Carnot map. It has 6 variables. It has 64 cells. And here every alternate cell is a 1. How many neurons will I require in the hidden layer? 32, right? So here you go. In general, if I have n inputs, in the worst case, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer. So although you can actually compose this whole function using just one hidden layer, that hidden layer is going to be exponentially large in the size of the input, right? What happens if I make it deep? Can you see how this would actually be reduced if I make it deep? Anybody? What is this function really?
We could have like a combination of 4 variables in one layer and add 2 more subsequent.
How? So I'll give you the hint, right? This is just W XOR X XOR Y XOR Z. XOR flips every alternate cell, right? This is U XOR V XOR W XOR X XOR Y XOR Z. And how many neurons did we need for an XOR? 3, right? I can do an XOR with 3. And I can do this with 3 neurons and 6 connections, or I can do this with 2 neurons and 5 connections. So you can actually go below 3, but I'll use the 3 example for now, right? So in that case, here's how I can do this. For every pair of neurons, every pair of inputs, I can compute an XOR. So first, W XOR X is going to be done by these 3 guys. Then that output is going to be XORed with Y, 3 more. So for every new bit that you add to the input, I'm going to require, here I have 4 bits. So I'm going to require 3 times 3 neurons. Here I have 6 bits. I'm going to require 3 times 5 neurons. So in other words, an XOR of n variables will only require 3 times n minus 1 perceptrons if I'm allowed to go deep, whereas if I'm fixing the depth to only 1, it's going to be exponentially large, right? So you see why. So single hidden layer will require 2 raised to n minus 1 plus 1. The final plus 1 is for the final OR neurons, whereas if you allow this to be deep, so this is going to be exponential in n, right? Whereas if you allow this to be deep, then you can do this in 3 times n minus 1. It's linear in n. The difference between linear and exponential is tremendous, right? So you can see why you need depth. But then it actually gets even better. The XOR is actually associative, correct? So if I'm doing an XOR, then I can, if I have something like this here, x1 XOR x2 XOR x3 XOR x4 XOR, and so on, I can group these 2 guys, and I can group these 2 guys in the same layer, and then I can perform the final XOR over these in the next layer, right? So if I do this pairwise, now observe something very interesting. First, I'm doing a pairwise XOR in the first layer. Then I'm doing a pairwise XOR in the next layer. Then I'm doing a pairwise XOR in the next layer, and so on. How many layers will I need for this network? Any?
The number of variables.
It's just log n, 2 log n, because you have 2 layers for each XOR, correct? So you're going to require only 2 log 2n. See, I very helpfully put this on the slide. And here's what is really interesting. Suppose I say you're only allowed to use 15 layers. I give an upper bound on the number of layers that you're actually allowed to use in your network. I give you an upper bound on the depth of the network, regardless of the number of inputs. What happens? In the best case, you can go up to the depth. Beyond the depth, you still have an XOR. At that point, it's going to blow up, right? So what this means is that there is a minimum, for a given input size, there's a minimum depth of the network that is required to be able to compute universally any function. And actually, I'm kind of partially lying, but this is true for XORs. And reducing the number of layers below this minimum will result in an exponentially sized network to express the function fully. So you see why depth is needed, right? Also, there's also a minimum number of perceptrons overall that you will require. If you try to go below the minimum number of perceptrons for whatever depth, for whatever width that for whatever depth you choose, then you will not be able to compute the function. In fact, for an XOR, if you miss only one perceptron in the minimum architecture, what will the error be? 50%. You miss one neuron, you're going to be wrong half the time. That's how bad it is, right? So just to give you an idea of the criticality, think about this. An XOR, you take away one bit, you're screwed, right? So just the criticality of the structure and the depth of the structure sort of comes across. Now, I've been talking about neurons. You should really be talking about the number of connections, because the actual number of parameters is the number of connections. And in this example, there are 30. This is the number that really matters in software or hardware implementations. And networks that require an exponential number of neurons can require a super exponential number of connections, because you have an exponential times an exponential, right, in the worst case. So deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using one layer, only one layer, even a fixed number of layers. And it gets worse. Suppose I have a function which is very complicated, but if you break it down, it's a lot of funky computation, and then at the end you get a bunch of outputs which must be XOR'd. So at this point, if you limit the number of layers you can have beyond this, again the network is going to blow up, right? So just as a note, I've been talking about the XOR. The XOR is a very special function that people who work on these problems like to work with. It's a parity problem. You're computing the parity of your input sequence. And the real statement is that any Boolean circuit of depth d, a fixed depth d, using AND, OR, and NOT gates with an unbounded fan-in, which means any single gate can take any number of inputs, must have a size 2 raised to n raised to 1 over d, right? That is the theorem. Alternatively stated, there's an arithmetic class of circuits called AC. AC0 is the set of circuits which are polynomial in size and fixed depth. You cannot compute the parity problem universally with a fixed depth network. If you limit the number of neurons in your network and you limit the depth, then you cannot compute parity, which means that at least on the parity problem, there's a law for the majority of problems, you're going to be wrong 50% of the time, which means you might as well just save yourself the computation and flip a coin, right? Now, this sort of comes across very nicely in the XOR, but to be clear, I'm just using although it looks complex, I'm using a very trivial example. The real statement, this is Shannon's theorem, it's very nice. It says that for n greater than 2, there is a Boolean function of n variables that requires at least 2 raised to n over n gates, regardless of the depth. What this really means is that for any reasonably sized n, say 10 dimensions, 20 dimensions, 30 dimensions, the majority of the functions will require an exponential sized network, which means that if you took 20 variables and you threw all 20 all possible functions of these 20 variables into a pot and randomly pulled out one of these functions, that function is going to require an exponentially sized network. And in fact, he showed that if all Boolean functions over n inputs could be computed using a circuit that's polynomial in n, then p equals np. So everything, if someday someone just comes along and shows that p equals np, then I have to discard this lecture. Now, so here's a summary. An MLP is a universal Boolean function. It can represent a given function only if it's sufficiently wide, it's sufficiently deep. You can trade off depth for exponential growth of the size of the network. And the optimal depth and width depend on the number of variables and the complexity of the Boolean function, where by complexity I'm speaking of the minimum number of terms, or the number of terms in the minimal DNF formula for the function. So the story so far, we've shown that MLPs are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine, but deeper networks may require far fewer neurons than shallower networks to express the same function. Questions, anybody? No? Okay. So moving on, here's another caveat. I've used a simple Boolean circuit analogy for explanation, but we are not really using Boolean gates. What we are really using are threshold gates, and threshold gates have a property that Boolean gates do not. Meaning you can compute, a single perceptron can compute the majority function. But if you want to compute a majority function using only ands, ors, and nots, that network is going to be exponentially large. So a perceptron really is much more powerful than a simple Boolean function, which is what fooled Frank Rosenblatt back in the 50s and 60s, because he saw that this perceptron could compute something that required an exponentially sized Boolean network, and he thought a single perceptron could compute any function at all. And that's what Minsky and Papert put to rest, right? So regardless of that, regardless of the fact that a threshold function is much more powerful than a simple Boolean function, for large n, for most Boolean functions, a threshold circuit that's polynomial in the size n at the optimal depth, if you just take away one layer, it can become exponentially large. This is the general, this is the lesson so far. Now, we've been talking about Boolean functions, Boolean inputs, Boolean outputs, because these are easy to analyze, but there's a whole class of formal analyses that actually looks at neural networks as arithmetic circuits. We won't get into that, but it's a nice segue into the next topic, which is how do these things function when you operate on real inputs? So we're going to look at MLPs, not as yes.
I have a very stupid question.
No such thing as a stupid question.
So the threshold, can we go back to last slide?
Yeah.
So the threshold circuit is called TC, but the Boolean circuit is called AC. Why there is A instead of E?
Arithmetic circuit.
Okay.
That's all. It's just terminology, right? AC threshold circuit class, TC0, AC0, they just have, there's a lot of study that has gone into these things. And if you look at circuit complexity theory or computational complexity theory, you run into these ideas.
So A here means
Arithmetic.
arithmetic.
Yes.
Okay.
Right. So, if anybody has their, can you shut your laptop at the back? Yes. Anyway, so if I'm wrong, correct me on Piazza afterwards. Again, I make plenty of mistakes. The one thing you shouldn't be ashamed of is correcting me. I should be ashamed of making mistakes. So feel free to point out any errata on the slides, any mistakes in anything I've said on Piazza after the class, right? Now, let's look at MLPs as universal classifiers. We've seen this. An MLP, when you consider an MLP as a function over real inputs, it takes a bunch of real valued inputs. It's going to produce, let's say, a Boolean 1-0 output, right? Now that's a classifier because it's going to say, does this input belong to a class or does it not belong to a class? So conceptually, you're really saying, does this input fall in this target region or does it not? Now the first thing we saw was that a single perceptron is a linear classifier. Why so? You're comparing the weighted combination of inputs to a threshold. If it's greater than the threshold, you're going to output a 1. If it's less, you're going to output a 0, right? And where is the boundary? The boundary is where the weighted combination of inputs is exactly equal to the threshold. That would be, so when I say summation wi xi equals t, that is the equation for a hyperplane. So you'd have a hyperplane of this kind, and the output is going to be 1 on one side of the hyperplane, 0 on the other side of the hyperplane. So in the case of two inputs, if I were actually to plot the function is going to look like this. It's going to be 0 all the way to the hyperplane, then it's going to jump up, and then it's going to become 1 on the other side. And then we saw, so this is a linear classifier. The boundary is a line. The boundary between the 1 and the 0 is a hyperplane. It's linear, right? Now, we saw why this linear classifier interpretation actually tells you, explains the inability of the perceptron to model the XOR. So consider this where all input outputs, or all the inputs can only take value 0 or 1. So in that case, all inputs are going to be on one of these 4 dots. If I draw a perceptron of this kind, which is 1 on this side and 0 on the other side, what is the Boolean function it's computing on these inputs? This is an OR, right? If any of the bits is 1, it's computing the outputting a 1. What about here? That's a NOT. And this is an XOR. And you can see why you cannot do it with a perceptron. It has to go up and then it has to come back down, whereas a perceptron will not do it, right? But then having seen this, we saw how we can compute more complex functions. Like I want a function which produces a 1 inside the polygon and 0 outside. So the way we would do it, I would have one neuron, one perceptron, which produces a 1 in the yellow region and the 0 and the white. A second one does the same thing for this edge. A third one does the same thing for this edge. A fourth one does the same thing for this edge. A fifth one does the same thing for this edge. And now, observe this very carefully. I have 5 neurons over here. Each of them is going to produce a 1 on one side of a hyperplane and 0 on the other side. At this point, all of their outputs are summed and compared to a threshold, right? What is the only region in which the sum equals 5? Inside the polygon. Everywhere else, it's going to be less than 5. We will see why this is important in a few minutes. So if I simply apply a threshold of 5, I'm going to get the polygon, right? So given this, once I can compose a polygon, I can compose more funky outlines, like this guy here, right? I can have one subnet computing the first polygon, a second subnet computing the second polygon. I can OR the two, and now I can get a classifier that's going to produce a function that's going to produce a 1 if the output is in the yellow region, 0 otherwise. But then I can make it more crazy, right? I can actually have all of these boundaries, arbitrary boundaries. And how would I do this?
Increasing the breadth.
Pardon me?
Increasing the width of the network. Or
Convex shapes. I can just chop it up into little polygons of this, polytopes of this kind. I can have one subnet for every polytope or the lot. And then I'm going to get exactly the boundary that I want, right? So we've shown that you can give me an arbitrary boundary, an arbitrary Boolean function of reals. I can compute it using a multi-layer perceptron, but it's not one hidden layer, right? Can I do this using just one hidden layer? So here is my question. Here's this much simpler thing. Can somebody tell me how I would do this using one hidden layer? It's a trick question. So here's how you can do it, right? Let's go back to simple polytopes. Now look at this guy. I'm trying to compose a diamond. To compose the diamond, I'm going to have 4 perceptrons for the 4 sides and a final OR. But then the real thing I want you to look at is these numbers. The sum over here is 4 over here. That is not important anymore. What is the sum outside the diamond? So see this, it's 3 in these bands and 2 elsewhere. The area of the bands where the sum is 3 is infinite. The area of the bands where the sum is 2 is also infinite. So if I go over the entire space and plot this sum, that is going to look like this guy. It's 4 in here, it's 3 in these regions, it's 2 in these regions, right? Now let me do this for a pentagon. When I do this for a pentagon, it's 5 here, it's 4 in these little triangles. Observe that the region where the sum is n minus 1 is no longer infinite anymore, it's finite, right? It's n minus 2 that is infinite. And here's what the sum looks like. It's 5 here, 4 in the star, 3 and 2 elsewhere. If I go up to a hexagon, it's 6 here, the area where it's 5 has become smaller. If I go up to a heptagon, It's 7 in this heptagon. The 6 region is finite, the 5 region is finite, the 4 and 3 are now spanning infinity, right? If I go up to 16 sides, you will find that only 8 and 9 are infinite, everything else is finite. If I go up to 64 sides, you see what is happening to the shape. So 1,000 sides, right? As you keep increasing the number of sides to this polygon, a pattern emerges, which is the area outside of the polygon where the sum lies between n minus 2 and n keeps shrinking. You're going to get either n over 2 or n. All other area in which the sum is anything other than these two begins to shrink. And in the limit, you're going to get this function. It's this crazy little function over here. And for a small radius, it's an almost perfect cylinder. So what this means is that if I have an infinite-sided polygon, or almost infinite-sided polygon, I'm going to have infinite neurons in one layer, and then I'm going to just do an OR. That is going to give me something that looks like a circle, right? But the magic thing is not that it gives me a circle. The magic thing is that at this, just before you apply the threshold, the actual function that you're applying the threshold on is itself an almost perfect cylinder. Does that make sense to you guys? Right? So that means that the function that you're applying this threshold to is going to have a shape something like this. Okay? And if I slice it from the top, I'm going to get a perfect circle. But this is really how magic happens. So the sum is n, now here the sum is n over here, n over 2 outside. I can subtract the n over 2 just to adjust things so that the sum is n over 2 in the circle, 0 outside. I haven't really changed anything. But then let me take 2 of these guys. I can position the circle anywhere, right? So suppose I take 2 of these guys with the circles at different locations. And then without applying the threshold, just over here, I take 2 of these guys and sum them up. What is the resulting function going to look like? It's going to look like 2 cylinders, right? Because the first cylinder is n over 2 inside the cylinder and 0 elsewhere. The second one is n over 2 inside a different cylinder and 0 elsewhere. If I add these 2 guys up, I get this crazy behavior where I just added a bunch of lines up and yet I got 2 distinct cylinders. I can now slice it from the top and get 2 circles, right? Using a threshold, which means now this is how I'm going to do this network. I'm going to fill it up with cylinders. And by increasing or decreasing the size of the cylinders and filling them more and more compactly, I can achieve arbitrary precision. Is this exact? It's an arbitrarily precise approximation. It's no longer exact, but it's an approximator, which is why when you read about these things, they will say the neural network is a universal approximator, not a universal function, right? You can approximate pretty much anything with arbitrary precision if you build a large enough network. So what this means is that MLPs can capture any classification boundary using just one hidden layer. So MLPs are universal classifiers. More importantly, one hidden layer MLPs are also universal classifiers, except, again, you're back to this, right? If I want to do this little function with just one hidden layer, I need infinite neurons in the hidden layer, and it's still I'm only going to begin to approximate things. Whereas if I add just one more layer or 2 more layers, the number of neurons I required suddenly became something in single digits. So that's how depth actually matters, even for non-Boolean functions that are not working on Boolean inputs but are working on reals. So there's a formal, of course, if you want to look at the formal arithmetic, which I won't go into, there's a great deal of analysis on this. Valiant et al., Leslie Valiant et al. Actually show that a polynomial of degree n, if you want a function that computes a polynomial of degree n, then if your network has depth less than log squared of n, you cannot compute it. And Yashua Benjio has a similar result. Now there's a lot of work, there's a lot of ongoing work on the trade-off of depth versus size in networks, but the basic concepts pretty much are what we just saw, okay? So, but then let's look at the worst case scenario. Let's look at a few examples, right? we're going to still use threshold activation networks. Here is a network. Here is a decision boundary that I would like on 2-dimensional inputs. I want the output to be 1 in all the yellow regions. I want the output to be 0 in all the gray regions. If I do this with only one hidden layer, if I do this naively, as we just saw, I would need infinite neurons, right? Naively. Actually, it turns out this is a bit of a cheat problem where you can do this much, much more simply, but if I were naive, it would need infinite neurons. If I did this with two hidden layers, two hidden layers, here's what would happen, right? It turns out I can do this with only 56 neurons. How so? Observe that this entire pattern is composed of 16 lines. So I can have the first layer with 16 neurons. Subsequently, how many boxes, yellow boxes do I have? I have 40 yellow boxes. So for each of these yellow boxes, I need 1 neuron, right? Because I'm composing 40 individual polygons. And then I'm going to OR the lot. So I need 16 over here in the first row, 40 in the second row, and 157 total neurons. So going from 1 layer to 3, 2 layers to 3, shrank the size of the network tremendously, right? But still, can I do this better than 56? Anyone? It's an XOR, right? If I think of all of these lines as just producing Boolean outputs, the rest of the network is just an XOR over those lines. And now I can use an XOR network, and in this case the XOR network is going to need 61 neurons, but then let me give you a more complex version of this guy. This one would take infinite neurons if you did this naively using one hidden layer, but it has 64 basic linear features, and then the next layer has 544 boxes, so I'd require a total of 609 neurons. Yes?
How do you find the first 16 basic feature in the layer 1?
So I drew the figure, so I know, right? We are not speaking of learning these things yet. I'm speaking of the capacity of the network to model functions. Right? We won't get into learning until the next week. But then if I do this using XOR, it's 16 neurons, so if I do this with 12 hidden layers, I just need 253 neurons. So it went from 609 to 253, right? And the difference in size between the deeper optimal XOR network and the shallower network is going to increase with the complexity of the pattern. So the number of neurons, now what I didn't point out over here is here, when I used 2 layers, it was still, considering that there are 64 inputs, you'd have thought that I'd need if I use only one more layer, I'm going to need an exponential number of neurons, right? That really isn't the case over here. Why is that? Yes?
Sorry to interrupt. I just got a quick question. Is there a logical relationship between, say, the depth of the deep neural network and the dimension of the, say, the boundary, the zoom boundary that you can represent? Because it seems like that if you have only one layer, you have a linear boundary. If you have 2 layers, then you can actually form some kind of 2-dimensional box boundary.
So you're asking a seemingly simple and actually a very difficult question. So quantifying these things is really challenging. And there are many different ways of doing this. It's still ongoing work. And so the most intuitive stuff that you can see is where you think of it in terms of topologies and how many disjoint convex-like shapes you can find, or how many disjoint regions you can find. But alternative analyses look at VC dimensions and such like. And again, there's a great deal of work on that I won't actually get into. Quantifying this is hard. So the best we can do is to begin formulating some kind of intuition for how these things trade off. Right? So the thing here is that if you look at the second layer over here, the second layer didn't require an exponential number of neurons. It required something that was quadratic in the number of lines. Why is that? The reason is that these neurons are not statistically independent. Meaning if I have 2 parallel lines, if I'm to the right of this line, I'm also to the right of this line, right? So it turns out it's actually exponential in the dimensionality of the space, the dimensionality of not the number of lines, it's the dimensionality of the space over here. So this is going to be exponential, it's going to be quadratic. But more accurately, it's going to be exponential in the number of statistically independent features that you find in the input. Right? So here is the actual summary. The number of neurons required in a shallow network is potentially exponential in the dimensionality of the input, or exponential in the number of statistically independent features. There's a hidden slide that I'm not showing. You should go over it, right? But the story so far, MLPs are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. MLPs are universal classification functions. We just saw that. Even a network with a single hidden layer is a universal classification function, but deeper networks may require far fewer neurons than shallower networks. And deeper networks could be exponentially smaller than shallower networks to express the same function. So let's look at the final topic, MLPs as universal approximators. We saw this in the last class, right? If I'm looking at just a function, scalar function of scalar input, they can always compute, I can always get this pulse-like output by just using two thresholds, right? But once I can do that, I can plug a whole lot of those guys in and approximate any scalar function. But then how would I do this for a multidimensional function? For a multidimensional function, it's not that trivial. For a multidimensional function, it turns out, if I have a function of two variables instead of one, it already becomes very complex. And so the way you would do it is first you remember that an MLP can compose a cylinder, right? So now I can fill the space with cylinders to different heights to approximate any shape. Again, now it's no longer exact, it's an approximator, but I can get arbitrarily precise approximation using a sufficiently large network. So the MLP is a universal approximator. Now, the one small thing, for this guy to work, right, what I was doing was just simply summing all of these outputs. There was no further activation. But in a real network, what you're going to have is that after you take this sum of all of these inputs, you would apply some activation on top of it, which could be linear, meaning just pass it through, or a sigmoid, or a threshold, or what have you. So different output neurons may have different activations. So here, what we are really stating is that the MLP is a universal approximator to any function from the domain of the inputs to the range of the output neurons. So the limitations are completely specified only by what inputs you use and what what the activation of the output neuron is. But regardless of that, eventually it's a perfectly decent universal approximator. Any questions? Okay. So the MLP is a universal approximator for the entire class of functions it represents, right? Now, let's look at some trade-off of optimal depth versus width in these cases. In the previous discussions, we saw that a single layer MLP is a universal function approximator. More generally, deeper networks will require far fewer neurons for the same approximation error and can be exponentially fewer, right? But what are the limitations? To see the limitations, let's go back and look at this very simple checkerboard, right? I'm still considering threshold activations at this point. So if I'm considering threshold activations, this network with 16 inputs here and 40 inputs here, for 16 neurons here and 40 neurons here, can perfectly well model this checkerboard, right? But then that means this network can represent this shape because it has sufficient capacity to model the network, model the function. What happens if the network doesn't have sufficient capacity? Not all architectures can represent every function. To see how this happens, let's take a look at this simple case where instead of having 16 neurons in the first layer, I have only 8 neurons in the first layer. I allow you infinite neurons in the second layer. But in the first layer, I'm only allowing you 8 threshold neurons. Can you model this function?
No.
Why not?
Bottleneck.
Explain. Anybody? Suppose I have only 8 neurons in the first layer. I allow you infinite neurons in the second. Can you model this function?
Yes, in the first layer, it lost some information, and the second layer only depends on this information.
The first layer has already lost information. You can never recover. So here, for example, let's say my 8 neurons captured only these lines, right? You're only going to be able to say whether you're on the left or the right of any line. Now, you have no way of recovering these lines downstream, right? So basically, those 8 neurons, if they happen to be like so, this is all the information you're going to have. There's no way you can recover the crosshash, right? Even if your 8 neurons were arranged like this, 4 this way and 4 that way, you still cannot recover. Why is that? So to see this, well, let's hold that thought for a second. Now let's go back and look at the second layer. I give you all 16 neurons in the first layer, but I say in the second layer you're only allowed to have 39 neurons. Can you model this function? It doesn't matter what you do afterwards, you cannot model the function, right? You will need 40 neurons in the second layer because the same logic passing down one more step, right? And that's because I'm using threshold functions. Let me explain how, right? If I have only 4 neurons in the first layer, let's say, each of these neurons is going to say whether the input is to the right of some hyperplane or to the left of the hyperplane. But it doesn't tell you how far you are from the hyperplane. So you will be able to say that, I'm to the left of this first guy, I'm to the right of the second guy, but you cannot say how far away you are from either of these boundaries. You cannot position yourself within those strips. That means it doesn't matter how much capacity I give you downstream, you will not be able to recover structure. It is not there, it's been lost. How would you change this? Any guesses? You can change the activation function. So if I give you a sigmoid, right? If I give you a sigmoid, this actually tells you it's graded, correct? So it tells you how far away you are from the boundaries. And now that you know how far away you are from the boundaries, you can, now downstream, you still have sufficient information to add newer boundaries, right? But then, here is what happens. This is what the individual sigmoid looks like. The sigmoid carries sufficient information in a small range around the zero crossing. If you go too far away, the information dies, right? So suppose you wanted to do one better than this, what would you do?
One quick question. When you do a sigmoid, you'll get only the perpendicular distance from
the boundary.
Yeah, you still won't know. You can, if you go back to the diagram, you still don't know whether you're in a gray square or a yellow square. So that information still doesn't help us place it in the right direction.
So the next level of neurons can use this distance information. You can think of these as a new coordinate system. So for example, if I can now begin looking at the value, right? And that value tells me.
Yeah, but still it's just a perpendicular distance.
It's not going to give you cross hashes.
You can't have like the distance in the perpendicular.
No, you cannot. No, you cannot.
Direction.
Yes, you're absolutely right. So again, there are all these limitations, right? Once you go below the capacity, all of these things can happen. But then suppose you wanted to improve over the sigmoid, what would you do? Tan H is still going to have the same problem, but you can use other guys, right? So if I use something like the ReLU, it tells me how far away I am so long as I'm on the right side of the boundary. If I use something like the soft plus, it gives me a notion of a distance, right? Now the ReLU is a problem, it gives you information only on one side. You can use something of this kind. The key point is the perceptron must mark a linear boundary. You don't really care how it behaves on either side of the boundary so long as it's predictable, differentiable, and consistent. The key factor is the linear boundary. So although we've been explaining everything in terms of thresholds, that reason is historical because that's where we came from when we first began modeling neurons. But once you come to the realization that what you're really modeling is lines, and you're fitting lines over the entire space to model functions, then you get a lot more flexible, right? And now, so something of this kind, for example, that's called a leaky ReLU. It tells you information on both sides of the boundary. It also marks the boundary. And you can have other such functions. So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded. But if I have only 4 neurons in the first layer, I'm going to need a great many more neurons. I'm going to need more depth to make up for it in the rest of the network to be able to capture the structure, but still you may end up benefiting in the total number of neurons. Yes?
In the previous example, so by the definition of MLP, the case layer can only use the k minus 1 layers information. But how about when case layer can use from 0 to the k minus 1 layers?
So the restriction that the information is passed in a strictly layered manner is very artificial. That's not required. The whole point is that so you have a valid point. If the input feeds to every neuron in the network, then these restrictions go away. But if the input feeds to a limited number of neurons, those neurons are the gate, right? Regardless of how you do it, so long as I can slice the graph, I have a gate.
So I'm wondering, for example, when the input can be fed into every neuron.
Then the restriction goes away.
Yeah, and in that case, will the number of neurons be decayed or reduced?
I haven't thought about it. Most likely, yes. Almost certainly. We should try to figure this out. Yes?
May I know the difference between the like redo and just times 1? I mean, no activation.
You don't get the linear boundary.
May I know why redo can give me I don't see it intuitively.
So the two are very different in the sense that the real point is the hinge. That hinge is going to be a line. So you have something happening at the line, at the hyperplane. Whereas if it's linear, there's no hyperplane, there's no single hyperplane that you're actually identifying using the activation. Right? So you say there's this hyperplane, there's one behavior on one side, another behavior on the other side. So you can identify the boundary between two behaviors. If it's just linear, that's gone.
Yeah, so this is how to say the modified version of redo, then I could at least recognize that there are 2 signs at least. Because the multiplier is different.
So the whole point, all of those actually end up in engineering the network. The key point conceptually is the ability to apply a criterion to find a boundary where the behavior is different on both sides. Right. So anyway, so in closing, we are speaking of the capacity of a network. The capacity of a network has various definitions. You have information or storage capacity, how many patterns it can remember, VC dimension. From our perspective, it is the largest number of disconnected convex regions it can represent. A network with insufficient capacity cannot model a function that requires a greater minimum number of convex hulls to actually than the capacity of the network itself. Right? So it can approximate it with error, but it can't model it perfectly, even if that function is perfectly modelable by a network. Now, in terms of the capacity of the network, there's again a great deal of work on trying to quantify it, mostly in terms of VC dimension. So many different results. Koran and Sontag had the first paper in '98, where they said that for units with piecewise linear activation, like ReLUs, the VC dimension of a network is proportional to the square of the number of weights in the network. Harvey et al. Had a more recent paper where the function is some W. It's complicated. The really nice paper that if you want to really read something that's understandable and still nice and intuitive and fun, I recommend that you read Friedland and Krell's paper on the capacity scaling law for ANNs. And they explain how the whole thing can be thought of in information theoretic terms and have some very nice examples to explain the capacity of a network. Anyway, I'll stop here. Here's what we saw. MLPs are Boolean functions. They're universal classifiers. They're universal function approximaters. A single layer MLP can approximate pretty much anything to arbitrary precision, but could be exponentially large. Deeper MLPs can achieve the same or even greater precision using much far newer neurons, which means the deeper networks are more expressive for any fixed number of parameters, a deeper network can model a larger class of functions with precision than a shallower network can. So, and then in the coming classes, we will look at how to train these networks. I'll stop here. Any questions?